All right, so I'm somewhat quickly going to look at some of the math we need to know in order to answer this question from the 2022 Canadian Senior Math Competition. Feel free to pause the screen if you're not familiar with the question. So I have a bunch of marbles and I'm drawing them one at a time. And I'm asked to find the probability that the red marble, or the color red, is the first one to do the first to have nothing remaining in the bag. So I'm pulling marbles out one at a time, 15 marbles total. And when I'm all done, there will be some color, either red, blue, or green, that sort of got exhausted first. So I pulled all the red first is what I'm looking for. So that doesn't mean I need the 3 reds, 1, 2, and 3. It just means that when I pulled the last red, there were still both green and blue in the bag. So that is an important way of interpreting like what the question is saying, is that when I pull my last red, I still have to have at least one blue and at least one green in the bag. So obviously there's interpreting the question and then there's what's the math we can do. So it's a probability question. So I'm going to kind of do a really quick run through of sort of the concepts that are actually primarily combinatoric concepts that we need. So first of all, probability. We all have, I think, the general concept of probability. Like for example, in this situation, 15 marbles, 3 red, 5 blue, 7 green. If I just say, reach into the bag, pull out a marble, what's the probability that it's a blue marble? So if I'm just going to take out one marble, the probability that it's blue, well, it will be 5 out of 15, which you could write as 1 out of 3. Because there are 15 total marbles available and 5 of them are blue. So that sort of lays out the fundamentals of probability. Probability involves counting how many possible outcomes exist. So the denominator of the probability fraction, so this is how we write it. It's the number of possible ways that this event or this experiment could result. So if I'm pulling out one marble out of 15, then there are 15 different marbles I might be holding on to. So that's called the sample space. That's what this S means. You don't need to know that. This isn't intended to be a lesson on it. But you count how many different possible outcomes entirely exist. And what goes on top is the number of different outcomes that satisfy what you're looking for. So here I was looking for a blue marble, and 5 of the 15 marbles are blue. So that's the basis for probability. It's just you're counting the numerator and denominator of a fraction. The problem, of course, is that in this question, we're pulling a lot more than one marble. We're pulling 15 marbles from the bag. So how do we know, ignoring the situation I want, which is that the red marble is the first one to be exhausted, just let's start by counting the sample space. If I'm pulling 15 marbles out of a bag, how many different ways could that happen? You know, red, red, blue, blue, green, blue, red, green, 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 blue, blue, blue. There's a lot, right? There's a lot. So we need to introduce ourselves to the concept of combinatorics. So combinatorics is the mathematics of counting things that are kind of too big to count slowly, 1, 2, 3, 4. So it's a system of ideas to help us count big numbers, like how many ways can I pull 15 marbles out of a bag? So I'm going to start with the basics, which is, I'm just going to go to the side here because we're going to have to return to that question. So all combinatorics start with something called the fundamental counting principle. And the fundamental counting principle tells us that if there are 2 events, event number 1 and event number 2, and I want to know the number of ways that event number 1 and then event number 2 could occur, I can multiply the number of ways of each event. Now, there's all kinds of important things to consider here, like the fact that these have to be independent events, or you have to consider if event 1 changed the number of things for event 2. So let me give you a really quick example. I have a bag containing a red marble, a blue marble, a green marble, and a pink marble. And I want to draw 2 marbles out of the bag, and I'm not going to replace the first marble. So the first event that I'm going to do is draw the first marble. And there are 4 possible marbles I could have. Once I've drawn a marble, so if I've drawn the red marble, I have these 3 left. If I've drawn the blue marble, I have red, green, pink. If I've drawn the green marble, I have red, blue, pink. What I'm trying to get at is that no matter which marble I drew for event 1, I always have 3 left when I go for event 2. So there will always be 3 marbles left that I could choose, and that will give me 12 possible outcomes of that experiment. Draw 2 marbles one at a time from this bag. By the way, if I wanted to replace the marble, so if I was doing these 4 marbles in a bag and I wanted to draw a marble, put it back in, and then draw a marble, then that would just be 4 times 4, because when I went to that second draw, there were still 4 marbles there. So that would be 16. So if we go back to this question, you might think that, so first of all, when I draw the first marble, am I replacing it? No, I'm removing it and it stays out, because otherwise there would always be 15 marbles, and at no point would any of the marbles be exhausted, right? Like I'd never take the last red if I'm always putting marbles back. So I have 15 events to do because I'm going to draw 15 marbles. So the first event, and I've got a little helper down here, draw my little lines here. I've drawn 15 of them. So the first time I draw a marble, there's going to be 15 marbles that I could touch and take. So there's 15 choices or possibilities for that event. Then when I go to reach the next marble, well, there will be 1 fewer because I took 1 out. So there are 14 marbles. Then when I go and reach in again, there are 13 marbles. Then when I reach in again, there are 12 marbles, and then 11 marbles, and then 10 marbles. And please don't disappear before I explain why this is not actually the number of events for this experiment, but it's where we're going to start. So this is what it would look like. Right? So just based on what we just talked about, there are 15 marbles and I'm drawing them one at a time. How many different ways could that happen? Well, it's going to be a big number, 15 times 14 times 13 times 10 times 11 times 12 and so on. And just so you know, yes, you could type that into your calculator as 15 times 14 times 13 times 12 times 11 times 10 and so on. But this comes up enough in the world of combinatorics that there's a shortcut for it. So I started with the number 15, and then I multiplied by every one less, like I multiplied in a row by every number all the way down to 3 times 2 times 1. So if that happens, like for example, if I had a question where I did 7 times 6 times 5 times 4 times 3 times 2 times 1, so that's the same pattern I'm looking for, all the way down to 3 times 2 times 1. There's a shortcut for it called factorial, which looks like this. So the 7 example I gave is 7 factorial. Here in the actual marbles idea, it would be 15 factorial. So that's what that exclamation mark means, and it's a button on your calculator. And so you can calculate that really quickly. Now, of course, when I type in 15 factorial, I get a number that is too big to be displayed all at once. My calculator gives me this, which is 1, 2, 3, 12. So how big is that? That's 1.3 trillion. It's big. That's a very big number. But it's not actually the correct answer, because the 15 items that I'm pulling out one at a time, they're not all identical to each other. Sorry, they're not all different from each other. So if I had 15 different colored marbles, then I could do this. But because I have 3 red, 5 blue, and 7 green, then there are some times when, for example, I pull out red, green, blue, whatever, and then there's another time in that 1.2 trillion when I pulled out sort of this red first and this red second, but nothing else changed. But that would be the same event because the red marble is identical to the other red marble. So in fact, this 15 factorial that I've written is the number of ways if all 15 marbles were different. But of course they're not. Some of them are the same. So what we need to do is we need to remove from that number, so from our 15 factorial, we have overcounted. So for example, there are 3 red marbles, and let's pretend the red marbles ended up in these spots. Oops. Sorry, computer just did a little woohoo on me. So let me just erase this. All right, so we've established that 15 factorial is sort of a starting point. But let's talk, for example, about the fact that perhaps in one of those 1.3 trillion possibilities, I got a red marble in the 4th spot, a red marble in the 7th spot, and a red marble in the 11th spot, right? And then green and blue are elsewhere. So the problem is that if I exchange this red marble with this red marble and do nothing else that's different, move no other marble, then I've counted it here as a different occurrence. But in fact, it's not a different occurrence because those are the same red marbles. So what we need to do is we need to adjust our number for the fact that there are 3 red marbles. And anytime I could leave everything else alone and just pick up the 3 red marbles and mix them around, I don't want to count that. So I don't want to overcount. So what I have to do is I have to adjust by dividing by 3 factorial. And that 3 factorial represents the fact that every time I've pulled out a bunch of marbles, there are 3 of them that are identical red. And so these 3 marbles amongst themselves can be arranged in 3 times 2 times 1 different ways. So there are 3 choices as to which of my red marbles goes here. Then there are 2 choices as to which one goes here. And then there's 1 choice. But in fact, I don't want to count those 6 choices. I only want to count one of them because it's the exact same thing. There's a red marble 4th, a red marble 7th, a red marble 11th. So I need to remove all the times that I let the red marbles mix around with each other. So that's why I'm dividing that 15 factorial by 3 factorial. And of course, I need to do the same thing for the blue. There are 5 blue marbles, and for example, in some of the 1.3 trillion outcomes, I have blue marbles in those 5 positions, but I've counted as a different event all the ways that these blue marbles could be intermixed around with each other, despite the fact that that wouldn't look any different in terms of my outcomes. So I also need to remove from my 1.3 trillion the fact that there are 5 identical blue marbles. So I'm also dividing by 5 factorial. And of course, as I'm sure you can predict, I also have to do the same thing with the green marbles. There are 7 green marbles. So I need to remove from them the fact that there are 7 identical green marbles. So the total number of ways that I could reach into the bag, pull out 15 marbles one at a time, so here I am, and I'm trying to use brackets in your, you don't want to do 15 factorial equals, right? So I'm using brackets and I'm typing it in all at once. So my entire denominator is in a bracket, factorial times 5 factorial times 7 factorial. So I get 360,360. That's an awful lot less than 1.3 trillion. So that, ran off screen there. So that is the bottom of the denominator for us in this question. That is the total number of ways that you can pull 3 red marbles. Sorry, 15 marbles, where 3 are red, 5 are green, and 7 are blue. And I'm just going to pause for just a second, again, leaving that question behind, and just give you a completely different question just so you have an idea. If I wanted to count the total number of rearrangements of the word waterfall, so if I have these letters and I want to rearrange them into something called an anagram, just rearrange the letters, then I would say there are 9 letters in total, and I'm rearranging those 9 letters. But there happen to be 2 of them that are A's, and there happen to be 2 of them that are L's. So that's what that would look like. So again, it's the same math concept. I'm rearranging a set of objects. It's just some of them are identical. So let's go back to here, where we've discovered that the bottom of our probability fraction is going to be 360,360. So now let's talk about how you might actually approach this question, which is going to involve another type of combinatorics called choosing. So I'm going to talk about that for just a second. So we've mentioned what, for example, let's look at this. B, C, D, E, F, G, H. So here's 8 different things, all right? So you can pretend there are 8 different colored marbles in a bag, or 8 letters, 8 different things. And if I wanted to rearrange or draw one of them at a time out of a hat, or line them up in order, basically if I wanted all 8 things to be arranged, in math that's called a permutation, when you arrange objects. And if I'm rearranging all 8 objects, it would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, because there's 8 choices as to what goes first, and then 7 choices, and then 6 choices, and so on. We've already talked about how that's 8 factorial. What if I only wanted to arrange only 5 out of 8? So for example, I only want 5 of these, but I want all the arrangements that I can possibly make out of every group of 5 I could possibly make. So for example, I want A, E, B, H, G, and I want D, B, G, C, A, and I want every possible 5 I could get. So this is, again, going back to fundamental counting principle. Which one am I going to pick first? Well, there's 8 choices, and then there's 7 choices, and then there's 6 choices, and then there's 5 choices, and then there's 4 choices, and then we don't have the rest of it. So like it's not technically 8 factorial, but what we can do is we can acknowledge that what we're missing is 3 factorial, right? 3 times 2 times 1 is what's missing, and that gives us this, that I have 8 objects and I want to arrange 5 of them. Then what happens in the denominator there, what I'm dividing by, is the stuff that doesn't get arranged. But that's not what we need, but I will tell you that that is also a button on your calculator. It probably looks like this, or it might look like this. So for example, to do 8 times 7 times 6 times 5 times 4 and stop there, you do 8p5. So you have 8 different objects, permuting them, arranging them into 5 spots. We don't need that information. What we need is sort of the next step from this, which is if we go back up to our 8 objects, I have 8 objects. They're all different. What if I wanted to select 5 of them, but I don't care about the arrangement? So for example, if I selected A, E, B, H, G, it doesn't matter if I selected A, then E, then B, then H, then G, or if perhaps I did E, B, H, A, G. I would consider those to be the exact same selection. So we call this choosing, or more formally combinations. But how do I choose without arranging? So choosing without arranging, that's what we're going to need in order to answer the question we're working on. If you are n different objects and you want to choose r of them, the formula looks like this. So you notice everything always kind of goes back to factorial, and that's because factorial goes back to fundamental counting principle, which is fundamental to learning how to count. See, math good. And then we're going to do this, because if you remember, that's part of permutations formula. And then we're going to do this. So this extra business here, what it does is it removes from our count all the ways that we could order the things we selected. So that's the formula for choosing or combinations. But, we're less likely to use a formula and more likely to use a button on our calculator. Hold on, I'm having issues here with my mouse, and my number pad is causing me grief. Fix it. Okay. So what you would look for on your calculator, very close to where you found that button, assuming you did, is the C button. So number of objects, choose this many. So 8, choose 5 of them is how many groups of 5 I can make out of 8. Instead of how many arrangements of 5 units in length can I make? So we need that choosing information. Oh, one more thing. Again, your calculator might say NCR or CNR, but it's actually quite customary to write it like this, which is sort of like in a bracket, and I've just stacked the two numbers. So I would write 8 choose R. And so that's the notation I'm familiar with. It's the notation I see almost everywhere. I think it's the notation used in the answers or the solutions to this problem on the website, CEMC website. So I'm just going to use that. And why do we need to learn how to choose? So this is now the part where I actually answer, like, don't teach and just try to answer this. So, you can't really teach someone how to figure out how to solve every problem, right? You're never going to see this exact problem, but I'll just go through the steps anyway. So one way of interpreting what I'm looking for is that I cannot have a red marble last. So that means I can have either a blue marble last or a green marble last. So let's say it's a green marble last. So I'm going to put a green marble last. Because again, if the red marble's last, then I haven't done what the question wants me to do. So once the green marble's last, I don't really care where the other green marbles happen. They can happen, all 6 of the remaining green marbles could be the first 6. I don't care. I'm making sure there's a green marble last. So that means from the 7 green marbles, I've used one of them. I've locked it in place. I want it last. So there's only 6 left. And now I need to just choose which of these 14 remaining positions I could find the green marbles. So the way I've set up my line here, in case that's not obvious, is this is going to represent the first marble I've drawn, and this represents the last marble out of the 15 that I've drawn. So because I'm forcing a green marble to be last, I've got 14 positions available, and I've got 6 green. So I'm going to choose 6 spots to put green marbles in. So for example, I might choose these 6 positions to put the green marbles in. That's one thing I want to consider, is all the different ways that the green marbles, the 6 green remaining marbles, could go. Here's another one. I could put the 6 remaining green marbles in those positions. And so what I need to do is figure out how many different ways could those 6 remaining green marbles go into 14 positions. So I'm going to re-ask that. I have 14 positions, and I need to choose 6 of them to write a green marble in. So I would say 14 choose 6 is me choosing where to put green marbles. So I'm just going to write at random one of the possibilities as to where the green marbles went. So there's one possible outcome of the 14 choose 6. Oops, 14 choose 6. Nope. There are 3,003 different ways that I could choose which locations to have green marbles. So again, locking one of them there, I must put a green marble last according to my current logic. And so there are 3,003 different places, different ways that I could arrange the other 6 ones. So once I've done that, no matter how they're arranged, there's going to be 1, 2, 3, 4, 5, 6, 7, 8 positions left to consider. So now I'm thinking about those 8 positions and the fact that I still don't want this one to be a red marble. Because if it's a red marble, then the blue marbles got finished first. So now I'm going to force this one to be a blue marble. So that marble here, whatever the last available position is. So really, I'm only thinking about the 8 spots that are available, numbered in red. I'm not even considering the 7 I've already filled in with green. So this last position, the 8th empty position, or the last empty position, I'm going to put a blue marble there. Done. Locked in place. Now I started with 5, so I now have 4 blue marbles, and I don't care where they go. They can go in any of the remaining 7 positions. Again, this one's gone because I put a blue marble there. So there are 7 positions remaining and 4 blue marbles, and I don't care where they go. So I'm going to choose from the 7 positions. I'm going to choose 4 blue marbles. 7 choose 4 is 35. And now I've placed 4 blue marbles somewhere. So, for example, maybe I put a blue marble here, a blue marble here, and a blue marble here. Oh, wait, one more, and a blue marble there. So what am I left with? Well, I'm left with 3 positions that I have not put a marble in yet, and I've got 3 red marbles. So obviously, the last thing I'm going to do is there are 3 empty positions. I'm going to choose 3 red marbles. Well, that happens to be 1. So in order to get a green marble last and not have the reds be second last, quote unquote, then there are 3,003 possible ways of putting the green marbles. And then there are 35 possible ways of having the blue marbles, and then 1 way of having the red marble. So altogether, there are 105,105 ways of arranging the marbles or pulling the marbles so that there's definitely a green marble last, and there's definitely not a red marble in the second last position. Meaning there's a green marble last and the blue marble ends before the red marble. No, backwards. You know what I mean. But I'm not done yet. Because that's fine. That's what I want. But that one says I must have a green marble last. Why can't I have a blue marble last? A blue marble last I could also do. So I'm going to sort of redo all of this. But instead of starting with a green marble last, I'm going to start with a blue marble last. So here we go. Let's see. I'm going to write, nope, I'm just going to erase. You can pull back the video if you need to see that again. I don't need to recopy that for you. So again, I'm going to rethink this, and I'm going to copy the number that I had, 105, 105. Okay, so now we are going to force a blue marble to be last. We definitely don't want it to be red. Once I put a blue marble last, there were 5 to start with, so there's 4 more blue marbles, and as we saw before, there are 14 empty positions, and I need to place 4 blue marbles. So I'm just going to choose from the 14 empty positions. I need to choose 4 of them in order to put a blue marble on it. So for example, this could be blue, 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 blue. That's one option. Keyboard's not responding. I might be about to glitch out. Hopefully I can finish the video. There we go. Bye-bye. Another option is blue, 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 blue. So think about all the ways that you could write 4 blues onto the 14 spaces. It's a lot, and we can calculate it as 14 choose 4. There are 1,001. So let's say that we put a blue marble here, 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 and here. That's one of the 1,001 options. So we've got all 5 blue marbles located. Now, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 empty spaces where I need to pull a marble. So whatever the 10th space is, whatever the last empty space is, so I'm now only worried about 10 spaces because I've filled other spaces. I need that to not be red, so I'm going to make it green. So I'm forcing that one to be green wherever it is, the last available spot, which means I've now got, instead of 7 green marbles, I've only got 6. And I have 1, 2, 3, I've got 9 spaces left to put the 6 green marbles. So for example, green, 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 green. That's one example of where I could put 6 green marbles into those 9 spots. So the math would be 9 choose 6, and 9 choose 6 is 84. And once I've done that, I have 1, 2, 3 empty spaces where I can put the red marbles. And because I forced the blue marble here and the green marble to be there, like the last empty spot, then I know I'm not going to end, I know that I must pull all the red marbles before the final green and the final red. So again, we know that 3 choose 3 is 1. So the total here is 1,001 times 84 times 1, which is 84 0.084. So this is the total number of ways if blue is last. This one, the 105, 105, is the total number of ways if green is last. And I do not want to put the red one last. So if I add those together, I'll have the total number of ways of pulling the marbles, pulling the 15 marbles, ensuring that the green one, ensuring that the red one, I've pulled all of the red ones before I finish pulling the green and finish pulling the blue. So I get 189, 189. So probability is the number of ways the event can happen, 189, 189, over the total number of ways that the whole thing could happen. And so that is the answer to that question. Apparently it reduces. I don't know if my calculator is going to reduce that nicely. 21 out of 40, which is the answer. Hooray. Yay, math.